7.3, operational properties. Here we'll talk about two main concepts. The first is called the first translation theorem, and the second one, second translation theorem. So, and a couple of days ago, somebody had a neat idea of having to solve a Laplace transform that had like a combinational functions involved in it, and you were dead on the idea of what we mean by the first translation theorem. The first translation theorem says that if you have the Laplace transform of a function f of t, and then also if you see in there some e to the at, so if you looked at the integral of that, it will work itself out. Let me scroll down. It would work itself out in that you are making a shift from the so-called center at A, and so we're going to shift over from S to S minus A. Now what does that mean? It means this: if I take the Laplace transform of a function, some f of t, doesn't matter what it is, times, if the key is that you have this e to the at, Laplace transform of any function times some e to the at. If you have that, you take the Laplace transform of the function, and then you're going to translate the result of that. Wherever you see s, just write s minus a. So there's a shift, and here this particular example is for a positive, but a can be negative as well. So you could shift. It could shift to the left or to the right. It doesn't matter. Let's see if we can highlight this by looking at a problem. So what we're going to do here is I'm going to write this as the Laplace transform of t, and here s is going to shift from s to this e to the 10t. You know, if you were taking the Laplace transform of that, let's write Laplace transform of e to the 10t, you would write that as 1 over s minus 10. I'll tell you this. E to the 10t. You'd write this as 1 over s minus 10, right? So here s is going to shift from s to s minus 10. So the Laplace transform of t is 1 over s squared, where here s is shifting from s to s minus 10. So I have s downstairs, so I write my answer as 1 over s minus 10, all to be squared. So the first translation theorem says if you're taking the Laplace transform of any function times e to the at, you can make the shift from s to s minus a. That's all. So look at this one. This is the Laplace transform of that t to the third. Here, s is being shifted here from s to s plus 2, right? Because of that e to the negative 2t. So the Laplace transform of t to the third is 3 factorial all over s to the 4. S does a shift from s to s plus 2. So we have 6 all over s plus 2 to the 4th power. If they complicate it, the only thing that you want to be able to see is that it's the Laplace transform of whatever function times some e to the at. If you see that, you can use the first translation theorem. Now, the neat thing is that the first translation theorem and the second translation theorem basically have nothing in common, so you won't get mixed up. Do I use the first or the second? You will know to use the first or the second. So this is the Laplace transform. We're going to take that e to the t plus e to the 2t squared and just expand that out. And when I do that, just put a t in there as well. So this is t times e to the 2t plus 2t times e to the 3t plus t times e to the 4t. So you're going to do that in 3 parts. So this is the Laplace transform of the t times e to the 2t plus 2 times the Laplace transform of t times e to the 3t plus the Laplace transform of t times e to the 4t. So the Laplace transform of t is 1 over s squared. And the translation for this first one, bless you, s is going from s to s minus 2. This one, s is going from s to s minus 3. And for this one, s is going from s to s minus 4. So the Laplace transform of t is 1 over s squared, so this is 1 over s minus 2 to be squared, plus the Laplace transform of t, again, is 1 over s squared. There's a 2 sitting there, so it's going to be 2 all over s minus 3 to be squared, plus the Laplace transform of t again is 1 over s squared, but s is translated to s minus 4, so this is s minus 4 to the second power. Any questions there? Well, we know that the Laplace transform of sine 3t, well, that says it's the k over s squared plus the k squared. Well, here k is 3. So this is 3 all over s squared plus 9. But the s is shifting from s to s minus 1. This is e raised to the 1t. So s shifts from s to s minus 1. So basically, wherever I have s, I'm going to write s minus 1. So this is 3 all over s minus 1 to be squared plus 9. Is that okay? Again, doesn't matter how they complicate it. Let's break this down. This is really the Laplace transform of 3 parts there. This is the Laplace transform of cosine 5t minus the Laplace transform of e to the t times cosine 5t plus 3 times the Laplace transform of e to the negative 4t times cosine 5t. Now, the first Laplace transform will not use the first translation theorem because there's no e to the at times that cosine. So we just take the Laplace transform of cosine directly. So this is s over s squared plus 25. So minus, what I want to do here is just take for the theory for the first translation theorem says, take the Laplace transform of the function f of t and then after that, translate it, right? So the Laplace transform, again, of all three, cosine 5t, cosine 5t, cosine 5t would be the same thing. S over s squared plus 25. Here, s will go from s to, this e to the t will tell us it goes from s to s minus 1. Now folk like Wes and Fraja, they would have done all that stuff in just one step, and they would have been done, you know. But folk like me would have to do it step by step. You know, maybe something. The people that sit over there, they typically do really well. So, hey, guys, next time for class, we'll all just sit over there, right? You know, we don't sit on that side over there, man. No. So plus the 3, I'm going to associate that with the s up top. This is s squared plus 25. And then s here goes from s to s plus 4. So wherever I have s for those second translations, we're going to put s minus 1 for that second one, and then s plus 4 for the third one. The first one stays the same. Minus up top is s minus 1 all over s minus 1 squared plus 25 plus 3 times s plus 4 all over s plus 4 to be squared plus 25. So pretty straightforward. Now you have the first translation theorem. For each theorem, we can look at the inverse of it. And the reason why you want to look at the inverse of it is that when you get to solving for a differential equation using Laplace transform, that last step down there involves taking the inverse to be able to actually go from y of s to y of t. Right? Y of s is just the Laplace transform of y of t. So take the inverse of here of the first translation theorem. So this capital F of s minus a is the result that you would get from the first translation theorem. Take the inverse of that, and that's simply e to the at times f of t. So I'm going to kind of break that down into two parts to be able to show you. It's like two things going on, and it's always like that with the inverse. It's like two things kind of going on that you somehow submerge together to get your result. So, two things here. Notice the first, that the inverse of, if you look at this guy, there's two things going on. There's the inverse of 1 over s to the third. And then secondly, there's the inverse of 1 over s plus 2. Right? Well, since I'm there, break that down. What's the inverse of 1 over s plus 2? E to the negative 2t. Wes, are you familiar with Charles Bronson? It just dawned on me who you are. Charles Bronson was the tough guy back in the 80s, I would say, you know, in those cop movies. I mean, that guy was, man, he was something, man. He was like I think my mother. She loved any movie that Charles Bronson was in. And he played in some Western movies, and I thought it was kind of ironic that he was in a Western movie, because he's somewhat like, I guess maybe Italian background. I think he's from America, but you can kind of tell he's probably like Italian maybe. But check him out, Wes. That guy, he's tough, man. You kind of favor him, then you kind of sound like him. You got that voice. Charles Bronson, man. That guy, it was like Charles Bronson, Clint Eastwood, you know, back in the 80s. Those guys, they were raking it up, man. So So anyway, um, so that's the inverse of 1 over s plus 2. Now what's the inverse of 1 over s to the third? That's a 3. Cannot write small. All right, so if you think about it, if you had 2 over s to the third, right, then its inverse would be t squared, right? So here, this guy would have to be a 2 here, and then, say, divided by a 2 as well. So 1/2 times 2. What are we saying now? If you go the direct way, Laplace transform of t squared is 2 all over s to the third. So if you go in the opposite direction, just divide both sides by 2, so you get the 1/2, and so then you get what you need. So here, this guy is 1/2 times t squared. So the inverse of the first translation says that you got to have the e to the at. We got that down here. That's e to the negative 2t times the original function. The original function is 1/2 t squared. Right? So the answer here is 1/2 t squared times e to the negative 2t. Just submerge both of those parts, 1 and 2. Now to break this down, you got that s squared minus 6s plus 10. You want to complete the square. Why am I completing the square? This particular problem is either going to be a cosine or a sine. And for your denominator for the cosine and sine, you got s squared plus or minus, well, plus k squared for cosine and sine. If it's negative downstairs, it's hyperbolic cosine, hyperbolic sine. So you want to be able to build an s squared plus k squared from this s squared minus 6s plus 10. And the only way we can do that is to complete the square. And so this s squared minus 6s, I take half of the negative 6, which gives me negative 3. You square that, you get 9. So we're going to add 9. Since this is not an equation, I don't have the other side, I'm going to add 9 and subtract 9 right there. We subtract 9. And then I have the plus 10. So I take the first 3 terms, and you can factor that. That's going to be a complete, perfect trinomial, perfect square trinomial. So this is s minus 3 to be squared, and then minus 9 plus 10 is plus 1. So I have the inverse of 1 over s minus 3 to be squared plus 1. Again, 2 things that I want to be able to see. I see the inverse of 1 over s minus 3. That's e to the 3t. I also see the Laplace transform of sine of t. So if we do the inverse transform of 1 over s squared plus 1. Isn't that sine of t? So my answer, I put these two together. That's your answer. E to the 3t times sine of t. I hope that's not complicated or confusing. Right. But here, the inverse using that first translation theorem is going to be two parts, and you just multiply them together and you get your answer. Okay, number 15, again, we're going to complete the square here. Have s squared plus 4s plus 5. Now, I'll tell you this, just something on the side, that when you have a quadratic downstairs, and if you have a number upstairs, then it's typically going to give us a sign, because you can always manipulate the number upstairs. Because the sine of kt, the Laplace transform of that is k, which is just the number, over s squared plus k squared. So if you need a 5 up top, like if you have 5 over s squared plus 25, then you can put a 5 there and then divide out by 5. And so you have 5 divided by 5. So you can manipulate that for the sine. But for the cosine, you can't manipulate it. But the cosine will always kind of give you a clue that you're going to have an s up top. Because you remember that cosine, the Laplace transform of cosine kt is s over s squared plus k squared. So here, we're going to complete the square. I'm just going to go ahead and complete it right here within the Laplace transform. So this is s over, have s squared plus 4s. Take half of 4, you get 2. You square that 2, you get 4. I'm going to add a 4 and subtract the 4. That's plus 5 sitting over there. So this gives me the inverse transform of s all over s plus 2 to be squared plus 1. All right? Now here's where you have to use your magic math. Math, magic in it. You remember there's two things going on with the inverse for the first translation theorem. You want to be able to pull out e to the at, and then you want to be able to identify the function f of t. Well, here e to the at is going to be e to the negative 2t. And then the so-called function, it looks like it's going to be cosine, but notice up top I have an s, and downstairs I have an s plus 2. They have to be the same. So either you get rid of that 2 or you add a 2. Well, I can't get rid of the 2 downstairs and the s plus 2 to be squared. A lot of stuff going on there. It'll be easier to add a 2 up top. But if I add a 2, you just can't add anything just out the blue. You got to be a reason. You got to be justified, right? And look, and man learns that from the Creator, because everything that he does, he justifies, right? Sin is justified through repentance by blood sacrifice. That's the justification, right? I mean, that's a theoretical concept. That's the justification of sin. Sin must be punished, whether it's in God or in man. If I do wrong, my child does wrong, I'm going to get him. Somebody's going to get me. Police will get me, and they have. It doesn't feel good. But anyway, you got to go to court and pay that dang on traffic ticket. Oh, man, that's rough, So I'm going to add a 2, and at the same time, I'm going to take a 2 away. So we're going to say plus 2 minus 2. So I don't want to harm anything. I'm going to leave everything as it is, but we'll just use our math magic. Plus 2 minus 2. over s plus 2 to be squared plus 1. I'm going to break that down. This is the inverse transform of s plus 2 all over s plus 2 to be squared plus 1. Now the other guy I'm going to bring out, this is negative 2 times the inverse of 1 over s plus 2 squared plus 1. That second guy is going to give me a sine. The first term gives me the cosine. So hopefully you see it. In the translation, it's the result has to be e to the at. Well, this is e to the negative 2t. And then it's times cosine. Cosine of kt, well, k is this number here squared. That's 1 squared, so this is just cosine of t. Minus 2. I have this s plus 2, so that tells me that this is e to the negative 2t, and this looks like the sine of t. And all they're doing with these properties is trying to give you the understanding of how to be able to write your answer when you're having to solve a differential equation using the Laplace transform. If you think about it, these answers that we're getting right here looks like an answer from a differential equation. You remember that cosines and sines would be the complex conjugate, solutions for a differential equation with constant coefficients. And then you have this e to the negative 2t multiplied to it. That guy comes from if you're solving a differential equation with constant coefficients, and on that right side you have it's non-homogeneous. It looks like some e to whatever power over there. So you're just trying to build piecewise how those solutions are going to turn out when you're solving a DE using the Laplace transform. All right. Okay. 19. We're going to do. Time is getting away. Let's do 17. I'm going to skip 19. I have in my book 19 long, L-O-N-G. So skip that one. Time is of essence. All righty. This is s over s plus 1 to be squared. If the s up top wasn't there, I can just use that first translation theorem directly and get the result. But since that s is sitting up there, I can't break it down like that. But I can break it down by using partial fraction decomposition. So I have s over s plus 1 to be squared. This is a over s plus 1 plus b over s plus 1 to be squared. Remember that for partial fraction decomposition, when you have repeated roots, you list, if it's repeated linear roots, s plus 1 is linear. If it's to the nth power, you have to list it as a over s plus 1 plus b over s plus 1 squared plus, and so on, plus z over s plus 1 to the nth power. Right? So here this is s plus 1 to the second power, so we go out 2, but the repeated roots are written with the powers increasing, s plus 1 to the first, and then the next fraction, s plus 1 to the second. Multiply both sides by the LCD, you get s is equal to a times s plus 1 plus b. If you let s equal to negative 1 to cancel out the a, so I have negative 1 here for that, s is equal to b. Now I don't have any s to let to be able to solve for a, but no problem. When you have that, you want to write out both sides and then match corresponding parts are said to be equal for an equation. Right, so this is S is equal to AS plus A plus B. All right. This is 1 times S is equal to A times S. That implies that 1 is equal to A. You know, if you think about it, this is 1 times S plus 0, right, is equal to AS plus A plus B. Well, if both sides are said to be equal, then what's on the left must match up with what's on the right, of its form, of its type, right? So this is 1 times S is equal to A times S, so this implies that 1 is equal to A. Now I'm done. Now back in the old days when we didn't do the let S equal to negative 1, you'll say 0 is equal to A plus B. Well, indeed, if A is equal to 1, B is equal to negative 1. Good. So we come here. This is the inverse transform of A. A is 1 over S plus 1. And then plus B over S plus 1 squared. B is negative 1. So we say negative here times the inverse transform of 1 over S plus 1 to be squared. Okay. So on this first one, there's no second translation there. This is just e to the negative t. Minus, now this second one, there is a first translation that's going on in this one. 2 things is happening. I see the e to the negative t there, and I also see the Laplace transform of t. The Laplace transform of t is 1 over s squared. So this becomes t times e to the negative t. Now back in chapter 4, where you had repeated roots for a solution, where you had something like e to the negative x, and like c sub 1 times e to the negative x plus c sub 2 times e to the negative x as well. And if it's repeated, you remember we injected that times x, so that's what's happening right here. Remember, the t is x. Right? All right. Now, use the Laplace transform to solve the given initial value problem. And it looks like one of these problems will be the only one that I can do with the time. So let me pick one. Let me pick this one right here. This is the second order, so it's a little bit more involved. So I'll do this one, and then I'll be finished. It's going to take me over a few minutes, but I do apologize. And then on Monday, I want to finish this section. There's the second translation theorem that I didn't cover in this section that I'll finish, and then I will finish the next section, 7.4, and so the test will be on 7.1 to 7.4 for test number 5. So, and since the time is limited, we're just going to work it. Okay. So here, take the Laplace transform of this first term here. So this is going to be s squared times y of s minus s times y of 0 minus y prime of 0 plus 2 times s times y of s minus y of 0. Close that up. Now plus the Laplace transform of the y, that's just plus y of s. Okay, good. Laplace transform of 0 is just 0. So here I get s squared times y of s minus s times y of 0. Y of 0 is 1, so it's just minus s minus y prime of 0, that's 1, so minus 1, plus 2s times y of s minus 2, y of 0 is 1, just minus 2, then this is plus y of s is equal to 0. Get the y of s's together. So this is s squared plus 2s plus 1. Get everything else on the other side. This is minus s, which becomes s on the right side, minus 3, which becomes plus 3 on the right side. Okay. So then I have y of s is equal to s plus 3 all over. You can factor that guy while we're here. This is s plus 1 times s plus 1, or s plus 1 squared, if you will. Take the inverse of both sides, so I get y of t is equal to the inverse of s plus 3 plus s plus 1, all to be squared. And they don't give us any easy problems. We have to use partial fractions on this. So you have s plus 3 all over s plus 1 to be squared is equal to a over s plus 1. Again, my denominator is repeating roots, so this is b over s plus 1 to be squared. So multiply both sides by the LCD. That gives me s plus 3 is equal to a times s plus 1 plus b. Let s equal to negative 1, so that gives us a 2 is equal to b. And then notice here that 1 is equal to a. This is 1s, this is as, right? So I get 1 is equal to a. So come back here, this is the Laplace transform of the a, which was the 1 over s plus 1, 1 over s plus 1, plus the inverse transform of this b, but b is the 2, put it outside, times the inverse transform of 1 over s plus 1 to be squared. Now, this inverse of 1 over s plus 1, well, that's just e to the negative t. So we have y of t is e to the negative t plus this 2. Now, here I have to use that first translation theorem. The inverse of 1 over s squared is t, right? So that's the function. And then the inverse of 1 over s plus 1 is e to the negative t. So times e to the negative t. Okay? We'll stop there. Thank you.